Hi. Exciting morning already. So thank you for being here, and the presentation will be, will your protection systems work in the event of a cybersecurity event? So I'd like to share with you what I've been doing over the past 10 years, 15 years. In fact, starting back here with S4 in terms of starting me on that path for cybersecurity on protection systems. So some of the information I'm going to be sharing today really pertains to the power system, to the power grid, the electric grid, which is actually a grid of grids if you were to examine it. With respect to communication systems that operate on the grid and the protection devices on the grid, I wanted to share with you some of the constraints and design constraints that we have to work with in terms of the power system. Namely, the electric power, when you turn on your wall switch at your home, is basically instantaneously on. The electric power system is operating at the speed of light. With respect to that, the decisions that are being made in the power grid, in terms of all the systems involved, are being made so that they prevent unwanted grid states. That is, they prevent unwanted outages. They also make decisions to say, hey, I need to make a decision to create an outage in a localized area. So the devices and the systems and the design of those systems is something that myself and my team have been working on in terms of implementing good security practices and implementing technology with respect to the communication systems. But what you may not be aware of is, in terms of the communication systems, is that there are very specific requirements that the power grid is required to meet, both internationally and nationally. That is, the power system is required by the IEEE and the IEC to have specific performance requirements, latency requirements, as well as speed requirements. I'll talk to those in just a second. Besides the performance requirements, there's also a set of requirements, both internationally and nationally, regarding the quality criteria of the power system. In fact, if the power system goes down for any reason, there's a lot of paperwork that needs to be done in terms of investigating the cause or get to the root cause of why the power system went down. At Schweitzer Engineering, what we end up doing or saying in terms of when do I know I reached root cause is when I can turn the problem on and off again. My point here in terms of sharing with you is that there are design constraints for the performance of a system, the entire system, as well as quality constraints regarding the system. Layer this in also with the requirements for data communications to meet specific requirements, as we see here on the ANSI standard and the IEEE standards. That is, the data communication devices that are layered in with the security functionality and the protection functionality must interoperate within these requirements. Now, what I'm showing you here is a diagram to talk about the timing requirements. And when I say timing requirements, I'm talking about the timing requirements of a device, a relay device, and another relay device. Now, I need to explain to you what I mean by a relay device. Just in short, if you think about the circuit breakers in your home, if that circuit breaker trips, it is usually a result of overcurrent going through that breaker. Our relays that are used in the power system for protection of the power system is basically making those decisions and then communicating with one another to say, hey, should I trip, should I open up that line and cut power from that line? So there are specific timing requirements from relay to relay communications for various decisions that get made. I'm showing here a list of some of those requirements. Now, you may be saying to yourself, why am I showing you these requirements? One of the things Joel and Brad said earlier with Dale was saying, hey, how do we understand the functionality? What's the criticality of these systems? If I look at the transfer time classes TT3 and TT4, we see that the transfer time, the time between those two relays talking to one another, must occur within 100 milliseconds. So some of the functionality we're investigating and looking into, and I'll share more details in just a second, is trying to say, hey, the system requirements, the operational performance requirements of both the networking and the cybersecurity for the entire system must fall within this time frame. In fact, what I'm seeing in terms of the industry is since the electricity, that's power switch that gets turned on and off, operates at the speed of light, I'm seeing an increase in the performance requirements, speed requirements, latency requirements of larger system designs. So if I were to sum up a lot of these requirements in terms of performance and quality requirements, I listed some of them here, and you can see they're fairly daunting and challenging. Namely, if I see the network in the middle there, you see network recovery time required of 15 milliseconds, zero drop packets, uptime and expected life expectancy of 25 years. All these interplay into what I would call is a good and well-established design. So you may not be familiar with this, but this is a typical one-line diagram of a very simple distribution line. This is a power line, not a network communications diagram. What I'm showing here is what that distribution system would look like in terms of the power going through a line, and that the power system itself is saying, how do I minimize the outage to a smaller geographical area? So there are decisions being made, in this case I'm showing recloser controls, that are talking to one another and saying, hey, I don't want to take out that entire path, that entire loop. I want to take out maybe just a small part where the particular fault is injected onto that power line. So in terms of the way the system operates, think about it as microprocessor-based circuit breakers on a larger scale that are saying, hey, how do I minimize the outage that might affect a larger group of consumers, power consumers? Now layer onto this the networking requirements, and we'll see in just a second an example of that, and then layer into that as well as the cybersecurity requirements. I like the discussion this morning where the speakers are talking about, hey, we really need to understand the functionality of these devices, not in terms of just a higher level, but at all levels. I completely agree with that. In fact, here's a Purdue diagram, which we said may be dead. Now, in this case, I find it's a good diagram to have discussions with, to precipitate discussions. But what's the goal of the discussions? The goal of the discussions should be, as Ralph Langer said in his book some years ago on robust industrial cybersecurity systems, he said it must be robust. That is, the point of a system design where we start layering in cybersecurity is to make sure that we have robustness. I agree with the discussions this morning in terms of how they're saying we need to layer in functionality. And I don't want to imply on this diagram that this is what the entire system looks like. I'm just breaking this down into some simpler components for point of discussion with you. In this case, I'm showing higher level systems at an enterprise network connecting into SCADA systems. It might be HMI, might be a data historian, could be servers. I'll talk more about that in just a second. Going into a wide area network. The wide area network, I'm saying it could be TDM, it could be microwave towers, it could be even MPLS networks. Eventually, substation to substation to substation need to communicate with one another in order to isolate or reduce the fault area or the power outage area. Those systems, although not shown here, are saying, hey, this is looking at the enterprise talking or the SCADA level talking and saying, hey, how do I start intercommunicating from substation to substation to help make good, well-planned decisions? The other thing is, what happens as I start layering in to these systems at the levels, all levels, cybersecurity. The point is to start doing this with well-designed, well-intentioned efforts that are based on good engineering designs. So if I start layering in cybersecurity systems, I've got to make sure that they must not negatively impact the safe and reliable operation of the power system. And in that case, at all levels. So the other thing we need to do from a design constraint, besides the performance issues, we also need to understand what are the risks, what are the vulnerabilities and threats, what are the consequences. One of the things that I've seen in the 10 years, 15 years of working through this type of activity in cybersecurity with the SEL is that we are getting now much more information about the vulnerabilities. we're understanding more about the threats as well. So as we start learning more about that, we're going to need to really think through and think of the design of the larger system and what are those design criteria. Now, the screen is showing you some of the things when I say add-in security. What do I mean? What type of security am I talking about adding in? And if I start adding in these different security features, what sort of impact do they have in terms of the performance, in terms of the safe and reliable operation of the power grid? Not just one part of the grid, but the entire grid. When I say grid, I'm saying a grid of grids. So some of the things we've added in are domain controllers, file system backup recovery systems, syslog messaging, using Splunk to bring in logs, using VMs in certain layers, as well as using VPNs for encryption and authentication. One of the questions from a design perspective that was challenged to me by Dr. Schweitzer and Dave Whitehead, executives at SCL, they said, how is it that you know that what you're layering in isn't going to adversely affect the performance of the larger system, the protection system? So a good question, a good challenge. One of the things when we do design, this would be a way I might start drawing out network diagrams, and I'm saying, I think this needs to change. The way we draw clouds, the way we draw network diagrams, we tend to think we draw lands as clouds or boxes or tubes, and I'm saying what we really need to think about from our design perspective is what is the functional design specifications that we're really required to meet in order that the network meets the requirements, the operating requirements of the power system. So I think the diagrams do need to change, and I think they need to change in such a way that we get more information so that we make better informed decisions. So I'm going to show you an example diagram of something we've drawn up and explain it in a little bit more detail. Now, this particular thing, diagram, it's oversimplified, but what I'm trying to suggest here, from a network robustness perspective, and I'll add in security in just a second, but from a network robustness perspective, how do I design the network is as important in terms of adding in the layers of cybersecurity, in fact, affects cybersecurity. What do I mean? In the left side of this diagram, you see the switches. These are RSTP-based switches operating on a smaller substation network. What I do from a design perspective, or what we've done and what we've discovered in testing these systems is we've broken links, we've broken devices, and we simulated the breaking of these devices in a pseudo-operational environment, or a facsimile of the actual operating environment. And the question, and one of the things we've chosen to say is, from a design criteria, here's a question for you to think about. If you were to break a link on a network that you've designed, or maybe you're working in terms of consulting with a design, if you were to break a link, or if you were to break a device, how would the network traffic behave? One of the questions that was given to me by my manager was saying, hey, I'm going to break this link, Dwight. Now you tell me what the traffic's going to do. And I got to tell you, my first answer a few years ago on this was, well, I don't know. RSTP is just going to reconverge and figure out where to place the traffic. And he says, that's not acceptable. In a power system environment, you need to know where the traffic's going to go. You need to make the traffic predictable. In fact, when that link gets repaired, I want to know that the network will send the traffic back to the way it was. In other words, create a network pattern based upon path costs, root bridge priorities, quality, bits that we have available inside those switches and inside the routers as well, to say, hey, all the network traffic is always going to reside on the left side. In the event of a failure, I know the traffic and where it's going to go. That's a good design. That's a design criteria that you need to meet, was the challenge. So what we've been able to do is start testing that and start designing a network and saying at the outset, and working and communicating with our customers to say, hey, we know the traffic's going to behave this way because of what we've predicted in terms of design path costs for the network traffic, and we know in the event of a failure, we know where that traffic is going to go. So how do we do that? How do we verify that my design that's on paper actually works in practice. So one of the things we do is we do what's called hardware-in-the-loop testing. That is, we actually create a system, shown here on the bottom, is called an RTDS simulator. That RTDS simulator basically simulates the power system, the larger power system. In this example, a transmission power system. We're also showing how the protection systems, we simulate or have facsimiles of the substation, or multiple substations operating as well. Those 4 or 5 racks you see in the top picture are representing substation environment operating against a simulator. So from a power protection perspective, we're measuring the inputs that it takes, we're looking at the controller and the outputs, but we're also able to, with that simulator, inject faults. So we can simulate faults on the transmission power system and make predictions and actually watch the response of our system in terms of isolating traffic. Do we isolate the faults to the smallest geographical area? Now think about that a second. That's just testing the power system operation. How is the protection systems working for the power system? When I say protection, the relays that are protecting the power system. But what about layering in now, in this loop, our network switches, our network routers? What sort of latency and speed implications do they have in terms of performing in the presence of a fault? In fact, what you can start gaining from this is start saying, hey, I think I now can identify higher risk transmission substations because I see that these have more or potential implications regarding or consequences regarding failures or faults due to a cyber attack. So what you're seeing here is some examples of us putting together a large number of switches. The largest to date, I think I've had close to 300 switches put together and routers put together, operating against a facsimile of the substation environment. We're injecting faults on those systems. We're also checking the protection response time, but we're also looking at and introducing network failures. In fact, we're also able to layer in the security functions as well and increase the traffic burden on the network and watch how that negatively or potentially negatively impacts the operation of this power system and the power protection systems. Some of the tools we've been using, and these aren't all of them, but these are some of the ones I've looked at, and there's a couple I want to point out here. One I'll talk to in just a second, but one of them is our network link system. So how do I break a link and determine that the traffic hasn't been negatively impacted? So one of the things I've done is I've created a Linux computer that attaches to a switch where the power to that switch can be cut off based upon a connection into my computer. I'm able to, in real time, break that link and then determine and watch what happens to the packets and monitor the packets over the network. I'm also able to then, as you see here, the little power cord coming off, the white power cord in the middle picture, I'm also able to depict, hey, I can actually turn off an entire switch. So what I'm showing you here is a broad number of switches. We do them with multiple vendors and take a look at the impact of what happens if I start breaking links. What happens if I start breaking multiple links? What happens if I take down a switch? What happens if I take down a root bridge switch? So out of curiosity, I'd challenge you with a question. What are some of the more interesting constraints and significant constraints in terms of taking down systems? I'm just going to go over some of our findings here. So some of the findings that we've seen is root bridge and backup bridge are probably the more significant devices to really figure out in terms of design criteria. Namely, what do I mean by that? If root bridge fails on a power system network, what we're seeing is there's a very long speed and latency impact when those devices fail, as compared to a link or even dual links. We're also seeing that as we started adding in some of those security features I talked about at the levels on this network, those security features that I mentioned really have relatively little impact in terms of the operation of the grid. Network traffic loading is something I'll speak to in just a second, but we are able to load the network traffic significantly and test the protection systems and inject faults on the power system. So what does it look like in terms of we placed VM environments in multiple layers into the power system operation, simulating a larger power system with multiple substations. And what you're seeing here is some of the VM environments that we've used and some of the types of security features we've layered into this. What you're seeing in the green field here off to the right is a simple thing called multi-ping. We also have SolarWinds operating in terms of looking at network performance. So basically we create a network operations center or security operations center where we test these substation environments at the functional level, as Joel had shared earlier this morning. So what we've seen as we layer in these systems and actually say, hey, let's do a backup. Let's do an update to virus signatures, assuming that those virus signatures are clean. Let's start logging and increasing our Splunk information as we share information across the network so that we can understand what's happening to our power system from a network operations perspective. A lot of times the HMI systems really give very good information in terms of how the power system's operating. But the question from an operator's perspective, especially when these things are networked, is to say, okay, what is the communication system doing? Is your security system doing anything onto it, or the network doing anything onto it that's giving me false information in terms of how my power system, HMI, may be displaying information back to me? It's a very critical question they want answered, saying, hey, is this real, or is this something that's been caused by inadvertently by our security or networking, or is this a cyber attack? What I'm happy to say in terms of some of the observations I've made is that the security systems that get layered in generally don't negatively impact the operational aspects of the power protection systems. What I'm showing you here is Ostinato. If you walk out of these doors, I'd say this is a tool you should know how to use. It's a great tool. It was recommended to me some years ago by one of my customers that said, hey, this is sort of like Wireshark in reverse. What it allows me to do is build packets from the bottom layer all the way up, layer 1 all the way up to the layer 7. So I'm able to go in there and actually implement and send out packets through Ostinato, through my computer interface, and send them onto the network. So I recommend take a look at this webpage. If you're into wanting to test systems and burden networks with network traffic, this is a tool to consider. I'm showing you here in this picture on the right-hand side where I'm using Ostinato to generate packets. In this case, I'm generating packets at 500 megabits a second. Now, I got to warn you, if you start using this tool, make sure you figure out to turn it off, because I've managed to burn out a little network interface card on my computer, leaving it on all night without realizing it, and running at a gig wasn't the best thing to do for my computer. It got very hot, and it died. With respect to Wireshark and Ostinato, using both of those, I'm also able to look at and collect maybe off a span port or mirror port off my network and see a malformed packet. In fact, Wireshark is indicating here that I've got a malformed goose packet. So what I'm able to do is generate these packets, generate, in a way, cyber incidents that occur on the network, and it gives me a great deal of leverageability in terms of doing different things on the network that you may not have been able to do. One of the things I learned specifically on this is I tend to put in a payload on these packets with some of my initials on there, so when I do a Wireshark, I know it's me doing something and not someone else that's doing something to me. So that's something to consider as well. As I'm showing you here, I'm showing you we've burdened the network. We've implemented the cybersecurity solutions that are on the network, and we're showing that there's relatively little latency issues being shown here in terms of the green field that you're seeing there. Now, truth be known, let me share something I did with Ostinato that you shouldn't do, and I share this with you in a way just so to realize that you can test this yourself. And this is a challenge to you in terms of how a network operates. Ostinato gives you incredible capability to test that network. What happens if you were to send out a MAC address that's not on the network? What would RSTP do? I'll let you come back to me and ask me later maybe what it would do, but I can tell you it's not very fun to see. In fact, it caused a lot of consternation in a lot of customers' eyes to say, how did you do that? And I said, well, this is the way RSTP works. If it can't find a MAC address, it presents problems to all the switches that are connected to that network. It also suggests very clearly to folks that maybe having another layer of segmentation across the network is an important thing to do when considering power systems and the criticality of any infrastructure for that matter. So some of the quantitative measurements we're able to do. So what I like about what we're trying to do here, and what Dale has sort of challenged me some years ago, is to say, we're at one point understanding qualitative nature in terms of implementing security and robustness. But now, by breaking these links, by watching the system, we're able to move into an environment where now I have much more quantitative information that I can share with customers and say, here's quantitatively how the network performs. Here's what I can predict in terms of network traffic. Here's how I can show them where traffic will go on a network in the presence of a failure, in the presence of a device failure, and even give them quantitative information to say, hey, here's how many packets you might lose if this particular link goes down. And I can measure this over time because it's automated. I can measure thousands and thousands of these iterations of breaking links and build up a quantitative assessment of how the system uptime looks, downtime looks on various links on the network being broken. So when I start looking at some of the things that I've seen in terms of the results, I talk about load shed time. What I mean by load shed time is how quickly can a system isolate itself from the rest of the grid? How can the grid break apart into multiple islands and then recombine back together again in the presence of a large network infrastructure that we've been building? So we've seen, and the conclusion here that you should see is that different vendor devices vary in terms of their ability to shed that load. But also it depends on the quantity of devices that we're adding onto the network. So what I'm showing you here is various vendors, some of them doing well, some of them not doing so well. But the point is, I need to understand from the outset what are the timing constraints. I also then need to say, okay, how many devices am I talking about? What does the design look like in terms of on paper? What do I predict? What do I design in the network in terms of operation of these devices for load shed time as an example? I'll let you figure out who vendor S is. It's a blue line. I'll give you a hint on that. That's the color of my company, if you were wondering. So with respect to that, some of the final results. Network topology is key to robust design. Design, I would say, design operations and security so that your traffic is predictable. Root bridge depth is critical. It must be accounted for in a protection system or industrial control system design. If you're not doing that, you need to do that because it's a critical device in the construction of a network in a larger industrial control system. I'm generally seeing that protection operates well under network duress. So in general, I see that it operates very well. In terms of where to go next, where I'd like to go next, I really am looking at SDN. We're actively looking at SDN. We're looking and working with partners like Dragos and Nozomi and others for intrusion detection solutions, as well as starting to do intrusion prevention. That is, we actually take action based upon what we know as the threats and watching and changing potential outcome of consequences. So that's where we're going to next, and then I'm going to start layering in that as the next layer and start taking measurements and looking at and trying to get to quantitative results for our system designs. With that, any questions?
Thank you. Jacob Kitchell again with Accenture Security. This is the Q&A portion. Does anybody have any questions? Okay, while people are thinking, I have one. I've done some network testing as well, not as detailed or specifically focused as yours, but one of the questions I wanted to ask you was, how many iterations did you go through in designing and identifying your test cases before you stopped discovering new fantastic ways to break the equipment that you had?
Right. So the number of design iterations, that was a really good question. It ended up getting down to how long could I keep the customer focus on this. So the question really became turned around to what was the customer willing to accept in terms of how long he'd be. I would do it for a really long period of time and create a large number of cases. But at some point, the customers that we're providing these systems for are going to say, well, all I want to see is some of the worst case scenarios that you've uncovered. In general, we're looking at about 15 or so network systems, and what we've decided to go to in terms of solution of this is to say, we give the customer up front, say, we'll break a link, we'll break 2 links of our choice, we'll break a network switch of our choice, we'll test root bridge, and then we'll say to the customer, now what are your choices? What links would you like to break? We also then share with them, okay, here was our prediction of network traffic, and then show them the results of that network traffic. So to answer your question, not as many as I would want to do and have fun doing, but at some point, it's the customer that limits us.
Okay, hold on, here we go. Just introduce yourself.
Pete Anderler with Kimberly-Clark. Question around how you collected the data in your failures, if you're just looking at network or if you're looking at the VMware layer or other systems to see performance.
So we're looking at both in terms of failures, in terms of network. Typically, we're mostly concerned about network failures and network traffic failures, but we also attempted to precipitate failures on devices themselves. We use tools such as Nessus, Tenable's Nessus, to scan the systems. We injected, we actually had some third parties injecting Metasploit activities onto the network to test it in terms of how well is it going to deal with, I'll say, vulnerabilities due to cyber attack. So we also then would test hardening of the VM systems as well as in terms of these systems as network storage, such as NetApp. So we end up doing a number of tests that I didn't get a chance to really talk about because of the time limitations. But that's a good question. We do more than what I'm showing you here.